Further to that, I'm going to go back and sort of revise our thinking on how we create the initial bounding box, because it seems like quite a few of you were having issues with the bounding box. So we're going to kind of try to address that, and I'll do that right at the beginning. As I mentioned, assignment 2 is going to be due one class later, and I will update that in the syllabus/assignment sheet tonight. I just haven't had a chance to get around to it. So in the Dropbox, we have a grasshopper file. So in today's date, 0708 Voxels Part 2, essentially this is going to start off the class from where we finished the class last time. So we should all be on the same page. One other thing I wanted to mention is a few of you were also having issues with an intersection between your mass, so your solar mass, and the voxels, the centers of the voxels. And that issue seemed to be resolved, at least for some people, by upgrading from Rhino 5 to a demo version of Rhino 6. So for those of you using Rhino 5, I think at this point, I would just highly encourage you to use Rhino 6, the demo version. Please email me if this doesn't work for you and just let me know. But if you don't reach out to me, I'm going to assume that you all can use Rhino 6, the demo version, and with that you can work with Bison. Because I tried to come up with a contingency plan for those of you who couldn't use Bison, and it just wasn't the same. So please update to Rhino 6. For the remainder of this class, and if you're unable to do so, please email me. But otherwise, I'll assume you're using Rhino 6. So let's open the today's class file. Okay. Now, if you're using the site file within Dropbox, and you are also opening this Voxels Part 2, essentially what you're going to see is the subdivided shape like this. And then there's going to be the random calling leading into octopus like we did last class. Now I'm going to go ahead and open my notes just so I can sort of, follow where we need to go. Does anyone have any questions about anything while I'm opening this file? Yeah, Shri.
I had a question on the...
Oh, so the question, where can we find the latest site model? I just save over the previous site model. So it's going to be in that same syllabus assignments folder, island model and lots link. It'll just be under assignment site Rhino 5.
Thomas?
Okay. Oh, that is the wrong file. Okay. So the first thing I want to address, and I'll just maybe what I'll do is I'll just copy this file. Okay. So the first thing I want to do is I want to readdress a part of this definition. And I think that this isn't something that'll be totally unfamiliar to some of you if you've worked in Grasshopper for a bit now, and that's going back and revising your definition. And that's another reason why it's so good to label things. So in this particular case, it seems like the part of the definition that's giving a lot of people issues is this original bounding box. So for instance, we know that what this first group here, I've labeled it mass bounding box. What it does is it essentially takes our block outline right here. It chooses a segment from that block outline based on a list item definition. So that is somewhere down there. So one of these segments there. It will project that geometry to the XY axis down there. So that's what that is. From there, it'll take the endpoints and it will rotate this segment right there that we projected down around one of those endpoints. And we'll use those two lines to create a plane. From that plane, we create our bounding box. So that's the plane on which our bounding box is created. Yeah, so Shri, do you have a question still?
Yeah. Mine's from last lecture, the smaller than component.
Okay, we'll get to it after we revise this section if you still have one. So what we're going to do is we're going to replace all of this stuff. And we're going to do it in, maybe it's a different way. It's not better or worse, but I think it'll be a lot more robust for everyone. And I mean, you do this a lot in Grasshopper. If one way doesn't work, you just choose another way. It's no problem. So what we need to get out of this is essentially we need to get out a bounding box. And in particular, what we need to revise is the way we create the plane for the bounding box. So I'm going to propose something extremely simple. So if you're using the Voxels Part 2 file, what you want to do is you just want to ungroup this group that we had there. So I have my mass in isolation, and I have my bounding box component here. And what we're going to do is we're just going to delete all of these components here. So we're going to delete from our block outline to our construct plane component. Yeah, one. Okay. So anyways, what we will do is we'll just delete all of this. So, make sure you're in Grasshopper, and then we will delete that. And then you see what's going to happen is that our bounding boxes are going to rotate, and they're going to rotate to the original kind of XY plane. And who knows, maybe you want to have a bounding box kind of like this and have your voxels align in a different way. This actually looks kind of interesting to me. And the way we're going to form this new definition is going to allow us to do that. So very simply, what we're going to do is we are going to go to parameters, geometry point, and we're going to put that down on the canvas. I'm going to right-click this parameter, and I'm going to rename it to, I'll just call it bounding box plane origin. So kind of a bit wordy, but I think it's descriptive. And then what I'm going to do now is I'm just going to right-click the bounding box plane origin, or the line, or the point, and I'm going to go to set one point. And then what I want you to make sure is to go type equals coordinate. So yours might say, if you look at your command line, it might say type equals point. So just click where it says type equals point or coordinate, and just make sure it chooses coordinate. And what that allows us to do is it allows us to just pick any point in space. So you can see here, I'm just snapping to, a random curve. And that's good, because in this case, we don't really care where this plane is located, but we just want to locate it somewhere where it's visible. So you probably want to locate yours somewhere along your curve on your site. So I'm just going to snap to a kind of corner of my site like that. And now you can see that points reference. So that's a little bit different than maybe we're used to dealing with referencing geometry in Grasshopper, in that there's no Rhino geometry there, but it works just the same. It's also worth knowing that now you can use Gumball to move this kind of Grasshopper object around, which is kind of cool. So I'll hide that. Now, simply what I'm going to do now is I'm going to go to vector, plane, and then I'm going to go to XY plane. And then, so XY plane, it's just going to create a standard C-plane on the XY origin. But what we're going to do is we're going to change its origin to our bounding box plane origin parameter. So now you can see what we have here is just a little XY plane. So you can see the green line here is our Y axis, and the red line is our X axis. Switch to shaded. And now what we're going to do is we're just going to rotate it. And we're going to use this rotated plane to align our bounding box around our mass. So what we'll do is simply we'll go to vector, plane, rotate plane. Hover over it, just says perform plane rotation around Z axis. So that's great. So our plane will be our little plane that we've chosen there. Let's plug into the plane input. The angle, we will think about this in angles, not radians. So let's right click the angle and set it to degrees. So make sure you have the little degrees sign there. And then once we do that, what we can do now is we can just create a slider. So let's just double click on our canvas. And let's go -180.00 less than 180.00. So that just creates a slider from -80, 180, a floating point number with two floating point positions, to positive 180. So enter. We have this slider here, and we can plug into our angle. So now you can see what that does is it just moves this plane around. Okay. And now with this rotated plane, we can just plug this into the plane input of our bounding box. So we can just plug in. And now what we can do is we can just kind of manually rotate this till we get something we like. So for instance, if I want to rotate 45 degrees, I can do that. Now, if you want to get this bounding box perfectly aligned with one of your curves, what you can do is you can simply just in Rhino, you could just draw a straight line from your curve like so. So what I did there was I just went to the line tool. I chose a segment of my curve, and I just held shift to make sure I'm snapped to ortho, and I dragged straight up. Maybe I'll set to wireframe to make this a little bit easier to see. And what I can do now is I just make sure that project is on and planar is on, so we're not kind of skewing our angle in the YZ axis or XZ plane. And then what we can do is we can just go to Analyze Angle. And then start of first line will be this line we drew. Start of second line can be our curve. Draw it to the same origin. So our angle is 44.76, close enough. So if I want to be exact, I could just double click my slider and go 44.76 off of north. So the other kind of benefit about this method is, like I said, if you want to have skewed voxels that are skewed away from a curve, then you can easily, choose an arbitrary value like so, and that might be a design choice that you want to do. Maybe you think this looks better, and I'll leave that totally up to you. There's no right or wrong answer in that. It's conventional for a building to follow the curb, but in Ananav, conventions are, not taken too seriously. Unless it's FSR, then it's taken very seriously. So does anyone have any questions about that? I hope that kind of simplifies some of the issues some of you may have been having. And of course we can just group all this. And I'll right click this group and call it making a bounding box. So to those of you who raised your hand, do you have a question? Okay, so if that is the case, then I am gonna keep on moving. So I'm just gonna preview off all of my bounding box, my original one here. And if we go forward into our definition, where we ended up at the end of last class was we had, if you remember, all of these gene pools, all these genes which could sort of flick between 0 and 1. And effectively what this meant was that it's kind of hard to see here because, you know, it's just one unit. But somewhere, when I'm sliding like this, oh, you can see it move up there. You can see there's a unit up there turning on and off. So yeah, you can see that one right there. Each of these sliders corresponds to one unit. Now, if you're using my definition and you're using your own mass, you might have a different number of voxels than I do. So what you need to do in that instance is just make sure that you have the same amount of sliders as you do voxels, and to figure that out you can simply just hover over your call pattern list. So I have 1304 voxels here, and if you have two sliders like we do in this definition, you can see that the gene pool maxes out at 1,000. So my first gene pool has 1,000 values, which means I need 304 values in this second gene pool. So right now I have 264, which means I need to increase my number of genes. So I'll double click on that. It brings out the gene list editor, and I'll just double click on the gene count and I'll type in 304. Hit the check mark, click OK. So you'll most probably need to change that as well. Yeah, Erica.
My boxes in general have like disappeared since we did this new bounding box. It looks like it goes up.
Just 1 second, I think. Sorry. If you were speaking, could you speak again? I just realized that okay. Sorry. In changing my, so for everyone, for those of you who were asking a question before. In changing my audio setup, I switched my mic, and for some reason I wasn't hearing sound. But okay, great, I can hear people again. So ask away. Mm-hmm. Are you using Rhino 5 or 6? Okay. I will have to take a look at that during the break. And you said the previous version worked for you? Okay, well, for the time being, just switch back to the previous version, the one that's saved in the Dropbox then. Yeah. And for those who asked questions before, if you still want to ask them, I can hear you now, so please re-ask. Okay, I'll just leave it for the moment, but I can hear questions again. Okay, so we have all these units which we can switch on and off, and then we had defined our initial FSR. So in other words, if all of our voxels were present, so none of them were called, in this case, I would have an FSR of 20, which is, you know, twice as much as we're allowed to have in this site in Ananev. So, you know, the person developing this complex probably very happy, but the city not so much. We defined our max FSR and our minimum FSR, and we've set up a Boolean essentially limit switch that says it tests is our initial FSR smaller than 10, larger than 6. It combines those answers together to give us a single Boolean. So true if it satisfies both of these conditions. we've also here tested the FSR following our calling of the voxels, and that's how we're testing it against this Boolean switch. So what we're going to do now, before we bring up Octopus again, because like we found out at the end of last class, it won't really let you open Octopus unless you have a few more things in play. We are going to now add a solar calculation, and we're going to add that to the definition in order to try to balance solar irradiation, or how much sunlight this building gets, versus the FSR. And then we'll see how we can sort of use that to balance out the form. Yeah, question? Yep, that's fine. So right now it doesn't matter if Octopus is going to essentially switch off enough of these genes to, in your case, to satisfy that FSR. So we'll be working towards that. Yep. So what I want you to do right now is in Grasshopper, file open, and in our lecture files, under the which one was it? The building floor print solar. So 2006-22 building floor print solar. We're going to grab the solar envelope definition. So solar envelope. If you don't have that folder open, I'll also resave this in today's class folder. So I'll just save that in Voxels part 2. So I'll just save it as solar envelope. So again, that's just go to open document, go to today's class, which now has the solar envelope file, or go to the building floor print solar if you already had that downloaded, and grab the solar envelope file. So what we're going to do is we're going to reuse this component that we have here. So this is that solar component I made that we used to derive our solar envelope. So you also have this component in your solar envelope definition. So wherever you're grabbing it from, just make sure that you have the two dates here, the original Python kind of engine of the script, as well as the solar vector output. So just select all of these components like so, go Control C. If you're on a Mac, you might need to go edit copy, and then click on your upper right hand corner here. So this is something I do a lot in Grasshopper. I switch between definitions, and go to the definition you currently have open. So in this case, it's the program Voxels. And now what you're going to do is you're going to just go Control P or Control V, or if that doesn't work, just go edit paste. And you'll see that they sort of land where they previously located space in the previous definition. So we're just going to drag them sort of right below the two gene pools right there, because it kind of makes sense to put them right here, because they're going to be feeding into Octopus. So what we're going to do now is we're going to create a test. So we are going to essentially, we could do it for, you know, as many solar vectors as we wanted to. In this case, we're just going to do it for one, you know, moment, because we don't want to sort of crash our computers or wait for a long time for it to calculate. But essentially, we're going to try to balance the exposure to this one solar vector with the FSR. So the first thing we need to do is to choose one moment that we want to analyze. You can choose any moment, your birthday, whatnot. I'm just going to stick with March 19th because it's the first date that's on this slider here. So I'm just going to choose 2020 March on both. So you can just slide it like so, and then choose March 19th. Now you can see the analysis days output is 2020-03-19. Furthermore, we're going to change the start time and end time to be the same thing, just because we're just going to analyze one moment, right? I'm going to choose noon because it seems like a fairly, it's right in the middle of the day. The sun's at its highest level, more or less. So it seems like a good time to analyze. So I'm just going to double click that first panel, type 12:00, click OK. And then for the second panel, I'm just going to double click and go 12:00, click OK. So now we're analyzing March 19th, noon till noon, every 10 minutes. Doesn't really matter because, you know, it's just noon till noon. So there's going to be one vector regardless. And now what we can see coming out of here is we have just one vector. Now, again, a vector, if you just remember, all it means is it's a direction. So it's not a line, it's not a point, it's a direction. It takes the form of an X direction, a Y direction, and a Z direction. So if we want to preview that vector, kind of see where it's going, what we can do is we can just go to Parameters, Geometry, Point. We can right-click this point, and let's just rename it to Vector Preview Point. And like we did with our sort of plane revision definition we did at the very beginning of this class, we are just going to right-click this point parameter, go set one point. Make sure that type equals coordinate. If it doesn't, just click coordinate. Make sure that project and planar is off now, because you can see that white line indicates that Rhino is projecting to the XY plane, so I can just turn off project, and now it will snap to, you know, the curve or whatever snaps I kind of have on. And again, I'm just gonna, you know, snap to somewhere on the curb, just because it's, you know, within my field of view. And then now I can go to display, vector, vector display. I can set this vector preview point is the anchor. And what I'm going to do before I plug this solar vector into the vector is I'm just going to change its amplitude, because right now by default it has an amplitude of 1, and you can see that's kind of short. So what we can do instead, maybe let's, this point we can move it up using the gumball here so we see it better. So I'm just going to move this point up so it's sort of randomly floating in the air. What we're going to do is we're going to go to vector, vector amplitude, take our solar vector output, plug into the vector input, and the amplitude, I'll just right click it and I'll change its value to, let's say, 15. Click the check mark, plug that into vector, and now that just shows us the direction of our solar ray. So maybe if I want to move this point somewhere above my pile of voxels, it'll sort of give me an idea of what I'm dealing with here. So I'll make this vector even longer so we can see it better. So maybe I'll change the value to 40. Okay. So essentially what we're going to solve for, we're going to look at all the sides of the of this building. Maybe I'm just going to choose 2 sides, and we're just going to say, okay, given this vector, is this vector going to intersect with these sides? Or if we take this vector and try to hit each of, you know, these faces of the voxels, will there be shading? So will there be intersections between each face, the rest of the mass, and, you know, our hypothetical sun? So I'm just referring to my notes for what I did here. Okay. Now, I know one of these is wrong. Okay. So what we're going to do is we're going to find the center points of these faces right here. And there's lots of ways of doing this, but we're going to do something that's maybe a little bit more, I'd say, computationally light, but in Grasshopper it can be a little bit tricky to do. So what we're going to do is we're going to go to Surface, we're going to go to Analysis, and then go to Box Corners. So extract all 8 corners of a box. we're going to take, so I'm just going to move this vector and the amplitude to the side. Maybe I'll group it and just say, I'll call this group solar preview. What I'm going to do is I'm going to take these box corners. I'm going to move down all this solar stuff, so it's kind of out of the way. And what I'm going to do is I'm going to take my call pattern list. So this is the, oh, not there. Where is that? The call pattern list coming out of the gene pool. And I'm going to plug into box corners. So essentially what that's doing is it's giving me all the corners of all my boxes. So you can see all 8 corners of all these boxes. I'm going to right click the box input because you can see all my corners are sort of coming out in one list. So I'm going to right click the input and go graphed because I want all of these boxes to be looked at in isolation. And then furthermore, just for the sake of keeping the data kind of clean and more intuitive to work with, I see I have a leading 0, so 0, 0, 0, 1, 0, 2, 0, 3, etc., etc. I'm going to right-click the input and go simplify. And that's just going to drop all those leading zeros. So 0, 1, 2, 3, 4, 5, 6, all the way to 639. Now, what I'm going to do to figure out how to find the centers of the faces I want to analyze is I'm going to essentially average corners. Now, I did this little diagram here in the notes layer to explain what we're going to do. So if you go to your file, or if you have an old version of the site without this diagram open, don't worry, I'll go through it. But if you are working on this newest version of the site, and you have this diagram, feel free to just go into your top view. It's on the notes layer. If you have that layer turned off, that's where it lives. And essentially, I'm just showing you this to kind of explain how this component works. So if we look at corner A, essentially this is x min, y min, z min. So that means if we're looking at this kind of 3-dimensional voxel here, it means that x min, y min, z min is going to be this back corner. Now it's going to be this back corner in relationship to whatever xy plane defines this shape. So what I mean is we know that if we look down to the beginning of our definition where we created this rotate plane that defines our bounding box, so I'm just going to preview that on, we know that this is our x value here, this is our y value there, you know, straight up from this plane perpendicular is going to be our z-axis. So what that means is the x min, y min, z min is going to be this point right here. The x max, y min, z max is going to be this point right here. So what we're going to do now is if we look at this diagram is let's say we want to find the center point of the top face, then we know that we can choose, if we look at this little diagram here, we can choose, for instance, x min, because this is the x-axis, y min, because this is the y-axis, z max. So essentially this point is min, min, max. And this point here is x max, y max, z max, so max, max, max. And if we average these 2 points out, we get this top center face. Likewise for this side face, if we go x max, y min, z max, averaged with x max, y max, z min, we get the center point of this face. So that's what we're going to do, because if you hover over the box corners component that we just plop down on the canvas, you can see if we hover over corner A, for instance, it says x min, y min, z min, and that's what it's referring to. So x min, y min, z min is this point here. So let's go and look at our pile of voxels. And the first face we want to analyze to see if, you know, we can shoot a solar vector off of it and if it'll intersect with the rest of the geometry. Let's start with this face here. So I can consider this face my local south face. So in this case, it's going to be if I want to grab this point, it's going to be x min, y min, z min. So if I hover over my box corners, you can see this says x min, y min, z min. So we know that that's the point we want. So for instance, we can go parameter, or let's go math, utilities average. Let's plug in corner A into our average. And then you can see we have this point here. Now, when you average 2 points, so again, that was math, utilities, average, essentially what it's going to do is it's going to take the x value, average it with between 2 points. So if we're averaging between this x value and this x value, the x value is going to be this, right? So that's how we can average between 2 points. So if we want this center point, now we're looking for x max, y min, z max. So we're looking for max, min, max. So let's hover over our points. Max, min, min, nope. Max, max, min, nope. Min, max, min, nope. Min, 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 or min, min, max, nope. Corner F is max, min, max. So we want max, min, max. So we want corner F. So hold shift, drag corner F into the input, and now you can see that gives us the center point of this face right there. So does anyone have any questions about that kind of procedure for finding the center point of a box face? Is it just me, or is Thomas's cursor always a couple inches above where it actually is on the screen? Oh, wow, weird. No, Jeremy, that's strange. I look in the preview window, and that is bizarre. That is a canvas thing. Okay. Oh, that is so weird. Okay. Thank you for pointing that out. I am going to look into that. I doubt I'll be able to solve that on the fly right now. But yes, whenever I could see how that's confusing, just always, you know, I'll try to look at the preview window when I'm sort of pointing to a coordinate, but it might be kind of tough for me. So for like for instance, right now I'm on corner A. That's so bizarre. Okay. Yeah. Okay. So the box corners is corner A and corner F go into a average. So the average component's found in. Oh, and I'm gonna try to. Oh, that's so weird. Math, utilities, average. I am so sorry about that, guys. Yeah, I'll see if I can figure it out during the break. Okay, so we're going to try to figure out this center point. So now I'm looking at the preview screen. So this center point here, so that means we're going to average between this point here and this point here, which means that if this is our x-axis, that means max x min y, because that's our y-axis, and then min z. So we're looking for max, min, min. So let's grab another average. So math, utilities, average. So we're looking for max, min, min. So hover over corner A. It's min, min, min. Corner B is max, min, min. So that's the one we want. So corner B goes into the average. Okay, so you can see we have it right there. And now what we're going to do is we need to find this point right here to find this center point. So this one is max x, max y, and then max z. So max, max, max. So I believe that's G. Yeah, so G is max, max, max. So take corner G, plug into the average, and now you can see we get the center point right there. Okay, so we just need to do this for 2 more sides. So let's grab, we can just grab 2 averages. So let's go to math, utilities, average. put that down the canvas. I'm just going to go Control C, Control V to get these two more averages. So to find this center point right here, we want min, 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 and we know that's corner A. So take corner A, plug it into your third average. And then we want this point right here, which is min for X, max for Y, max for Z. So that's min, max, max. So that is, I believe, so here's another thing to throw a wrench in everything. I believe that the min, max, max corner is mislabeled, and I always forget which one it is. So you can just always go to parameters, geometry, point, and just plug the corners into the point. And it's, yeah, so corner H is the one we're looking for. So you can see it should be min, max, max. Instead, it's saying min, min, max. But we do want corner H. So just remember, corner H is actually min, max, max. So there is the most obscure grasshopper fact you'll ever hear in your life. So take corner H, hold shift and plug into the third average, and then that gives you the center point of what is our local west face. So right there. Now finally we want to figure out our local north face. So again, we can take our corner H, so let's go to our min, max, max, and we can combine it with our max, max, min. So min, max, max is corner H, so plug corner H into our fourth average, and then we're looking for min, max, min. So min, or sorry, max, max, min. So let's find max, max, min. So that is corner C. So take corner C, hold shift, and plug it into your fourth average. And that gives us our north face right there. So now, after we've done this, you can select these 5 components, right-click outside them, go Group, right-click this, and we can call this Selecting Side Faces of Boxes. Now, this might actually be a group of components that you want to, you know, save onto forever, so you don't have to do this kind of connecting the dots again. So does anyone have any questions about finding the center points of all our box faces? Okay. So from there, now what we're going to do is we're essentially going to draw this vector. So this solar vector that we have right here, we're going to draw it in reverse from all of these faces now. And then we can use those same vectors to see if they intersect with an overall mass. So what we're going to do is we are going to combine, just referring to my notes, yes, we're going to combine them all into one point. And we are going to, okay, good. So we are going to combine all of these into one list. What I mean is, since we've grafted these, you can see that we have one individual list for each face. So what we'll do is we'll go to parameters, geometry, point, and we'll just plug all of these averages into this one point component. And what this is going to do, so I'm just holding shift while I plug this all in, is if you hover over point, you can see now that there's 4 items per list. So what that means is each box has its own list, and within that list, there's 4 points. So if I click on the points, you can see all the center points are selected. So now I can preview off all of these faces. Now, what I'm going to do is I am going to essentially take these points and I am going to draw a vector from them, but first I'm going to move them first. So what I mean by that is, let's say, oh man, let's say we're looking at a box in elevation, right? And what we're going to do essentially is, here's our sun, And this sun, it's shooting out a certain ray. What we're going to do is we're going to look at this face, and we're going to say, this face is being hit by the sun, because if we reverse this vector and draw it straight back, it's not going to intersect with this geometry. But if we look at this face and draw a vector straight back at the sun, we say it's in shade because it's intersecting with the geometry, and therefore it's in shadow. Now, what we have to do before we perform this calculation is we need to offset our points by this vector. So what I mean is we'll take this point first, move it a little bit, take this point first, move it a little bit, and then shoot these rays out of it. And the reason why we do that is even though this point is, technically on this mesh and has a clear line of sight to the sun, because it's actually sitting on the box, Grasshopper is going to count that as an intersection. So even before this vector has a chance to shoot off into infinity or whatnot, it's going to intersect with the box. So that's why we have to move it just a tiny bit first, and then we do the intersection. So to do that, we have our vector right here. So coming out of our solar vector, what we're going to do is we're going to go to vector. We're going to go to vector amplitude. We're going to take our solar vector output and we're going to plug it into our vector input in our new amplitude. And if you remember from our vector display here for our solar preview, this display shows the direction of our solar angle, right? So the altitude and azimuth causes the sun angle to come down in this direction. Since this direction is, coming down, we need to reverse this. So what we can do is we can say, let's give this an amplitude of, let's say, we can set a number to be negative. So I'll say negative 0.1. So we're designing in meters here, so that's negative 10 centimeters. So again, amplitude equals negative 0.1. And now what we can do with all these points is we can move them. So we can go to transform, Euclidean move. We take our points, put them into the geometry, take our vector, put into the motion, and now you can see what happens is all the points just barely move off of the faces of the boxes. And that just, it more or less is testing the face, but it's just making sure this point is moving off so it doesn't intersect. And now what we need to do is we just need to test if this same vector shooting from each of these points intersects with the entirety of the mass. So is it self-shading? So what we can do now is we can go to intersection. Actually, before we do that, what we need to do is we have to convert all of these boxes into one single mesh. So very easily what we can do is we can go to parameters, geometry, mesh. So parameters, geometry, mesh. We can put that down on the canvas, sort of right above our solar vector and our box faces. And we can take our call pattern here, so all of our boxes, and we can just connect into the mesh. And what this is going to do, it's automatically going to convert our box geometry to simple mesh geometry. So you can see we have all these meshes now. Now the thing we want to do is, since it would take a lot of computing power to sort of say, okay, all vectors, check if you intersect with all boxes. So, it'd be 4 times 2,560 times 640. That's a lot. We can reduce that calculation by joining this mesh into one object. So to join meshes, it's very easy. We can just go to Mesh, Utilities, Mesh Join. So that's Mesh, Utilities, Mesh Join. We can plug those meshes into the meshes input. Let's preview off. And now if we look at our mesh output, it says 1 locally defined value. aka we just have one mesh. So after this, now we can do an intersection test. So we can go to intersect, mathematical, and then we will go to mesh ray. So intersect a mesh with a semi-infinite ray. It has 3 inputs, so the mesh to intersect is going to be the mesh we just joined, so plug that in. The point, so the ray start point is going to be all these moved points, so the points we slightly moved off of the faces. So like so, we can put them in. And then the direction is going to be the amplitude with which we moved all those points. So it's just the reverse version of the sunlight, right? Like we're just shooting a sun ray right back at the sun. So plug that in. And it might take a second to calculate, depending on your computer. But essentially, it's going to calculate if there's a hit or a miss. And you'll also see it'll tell you if there's a point. But we really only care about the hit or a miss. So for instance, if we grab a panel, so params input panel, plug the hit output into the panel, you can see false. You know, this face, I think it's this one down here maybe. This face, it's hit by sunlight. Whereas this face is not, this face is not, this face is not. So that's sort of what we're looking for here. So what we're going to do is from here, we're essentially just going to sum up how many faces are hit by sunlight. So essentially we're saying, okay, if we have 640 meshes and each of those have 4 faces, so that's 2,560. How many of those faces out of 2,560 have been directly hit by the sun at noon? So that's what we're testing there. If we want to test more times, you could. So for instance, I could increase this to noon till 1. You can see it gives me more testing times. And all that's going to do now is it's going to give me 7 values. But, if I were all of you, I would just kind of leave that for now. Like just stick with 1 time for this assignment. So, but if you do in the future want to test for more values, you can always just increase the analysis period. So what we're going to do, we have those 2,560 possible hits. We're just going to flatten the output. So you can see 2,560 results. And remember that trues and falses can, just be considered binary numbers, whereas false is a 0, true is a 1. So simply what we can do is we can add up the trues and falses. We'll add a 0 wherever there's a false, a true wherever there's a 1, and that will give me a single number. So what we can do is we can go to math, operators, mass addition, take the hit output, plug it into the input, and now this gives you a result. So this result here is 2,241. So what that means is that out of the 2,560, actually 2,241 are being hit by sunlight. So that's more than half. That is, first of all, kind of surprising. But, that is... Oh, you know what? It's the inverse, right? Because this tests if it did intersect. So what we can do, so again, you get a true if it's in shadow. Sorry, that makes more sense. What we can do simply is we can just go to, actually, we can just leave it like this. So it's kind of counterintuitive, but what this partial results will tell us, or this result will tell us, is it'll tell us how much of our building is in shadow. So in this case, it's 2,241 faces out of 2,560 are in shadow. So what we could do if we kind of want to make this a little bit more intuitive is we could just go math, operators. Let's actually go math, script, evaluate. So math script evaluate. Let's plug, let's go set list length. Let's take the hit output, plug into list length. So this gives us a value of 2,560. Let's plug that into variable, let's plug into variable y. Let's take the result of our mass addition, plug into variable x. Let's right-click variable x and just rename it to x. Let's right-click variable y and rename it to y. And the reason why we do that is just so we don't have to type variable x, variable y in the expression editor. Let's double-click the expression editor to bring up the expression designer. And to find the percentage, we can just simply say x, so the result, x divided by y times 100. So x divided by y times 100. I'll click OK. And this will give us the result. So I just plug that into the panel there. I can right-click this panel, and I'll just call it percentage in shadow. So that makes more sense. So essentially what this is saying is that noon on March 19th, you know, about 88% of this building is in shadow, which kind of makes sense, right? There's a lot of self-shadowing going on in here. So does that make sense to you guys? I know I kind of reversed the sunlight and shadow there, but essentially what this result will give us is the amount of shadow. And again, the reason why it does that is if it hits, it gives us a true. So you can imagine something that's in sun, if our sun's here, if we're testing for an intersection from this point shooting towards the sun, it wouldn't hit, so that'd give us a false. Whereas if something's in shadow, we're using that same solar vector, it will intersect, hit with the geometry, and that'll give us a true. So that's why trues equals shadow, false equals in sun. So does anyone have any questions about that? Okay, so if no one has any questions about that, what I'm going to do is I'm just going to the list length, the evaluate expression, the percentage in shadow panel there. I'm just going to group this. I'm going to right click it and I'll just call it percentage in shadow. So this is more something for us to sort of look at to get a better sense of how much of our building's in shadow. And then the rest of this definition, from maybe the solar vector amplitude to the move to the mesh join, all these components here, I'm just going to select them all, right click, go group. I'll right click the group and I'll just call this group figuring out the amount of building that is self-shading. Something like that. Okay. So now we can go back into Octopus. So if we quickly refresh on Octopus, essentially what it's going to do, why don't I just delete Octopus and let's just start from the beginning here. So I'm just going to delete Octopus right there. I'll leave the Octopus legend that we had made, but I'll just delete it so we can kind of start from afresh. I think it'll be a little bit more straightforward if we just rehook up everything. So just to review, Octopus is an evolutionary solver like Galapagos. So that means it uses iterations of a design. So in this case, the block of voxels based on these little parameters here, aka genes. And it will sort of quickly iterate through tons of different combinations of zeros and ones. It will choose the best iteration based on the criteria we've, set out here, and it will show you the results. So to use it, we go to Parameters, Utilities, Octopus. octopus is kind of a special component like Galapagos. So it has inputs, aka the genomes and parameters, which are essentially the things it can move, it can change, and then it also has essentially objectives. So these are what you call the fitness in Galapagos. So the first thing we're going to do is we're going to hook up the parameters. So in our case, our parameters are these 2 gene pools, or you might have 1 or you might have 3, who knows. So what we'll do is we'll go over to Octopus, we'll click on the G input, so the gene input, and like Galapagos, you click on the component and drag backwards, see the little DNA helix, and we'll clip it to our first gene pool. So you can see the pink arrow goes from Octopus to our first gene pool. We have to link it to our second gene pool, so I'll hold shift, click the little G till we see the green helix with an addition symbol, and drag it to the second gene pool right there. So now you can see those 2 gene pools are attached to Octopus. Yeah, Jeremy. Yeah, correct. Yep. So if you have more than 1,000 boxes coming out, you'll need 2 gene pools. If you have more than 2,000 boxes coming out, you'll need 3 gene pools. So there's a max 1,000 genes per pool, and you plug those both into the call pattern. So we've hooked the phenotype, or sorry, the genomes up to those 2 gene pools, and now we need to plug in the objectives. So the objectives in Octopus can be of 3 types. The first is going to be just a number. So our first thing we want to consider is our FSR. So you can see here, I have this reduced FSR panel, and essentially what that's saying is following the calling that takes place from these gene pools, our FSR is reduced. So what I can do is I can plug this into our Octopus by dragging out of the O, so the objective input, and dragging it onto the reduced FSR number right there. Yeah, Natalie. Mm-hmm. Yeah. Okay. So if that's the case, you could just try right-clicking the call pattern and going flatten. And does that solve your problem? Great. Okay, so that is something that I can check during the break or after class. Is one of those strange things I'll have to look at. But yeah, I think what Natalie did there, that she's referring to just hovering over the input and essentially seeing that she had, in my case, instead of having 1,304 values, maybe it just says 1,000 values. So that's always something to kind of check. One thing to mention is I can get rid of one of these gene pools, but what that means, and the reason why, Natalie, I say we'll worry about it later, is that essentially what's going to happen is that this pattern will just repeat. So when you have a call pattern, it repeats. So I only need to have 1 gene here, right? So for example, I could set my gene count to be 1. And then what that would mean is I have 1 pattern that's all off and 1 pattern that's all on. So that pattern will repeat, but still you want as many genes as you have boxes, just so Galapagos can sort of consider each voxel by itself. So we've hooked Octopus up to our reduced FSR number. So that's the first number we want to consider. The second number we want to consider is this result from our mass addition. So essentially this is the number we want to reduce. Now we could also consider this percentage and shadow number here as well. It doesn't really matter, because remember, Galapagos, all it's doing is it's trying to minimize numbers that you put into it. So why don't we take our percentage and shadow and plug it into Octopus? So to do that, remember Octopus is a little bit finicky. So what we're going to do is we're going to go to parameters, primitive, number. So parameters, primitive, number. Make sure you don't choose integer, but rather a number. And take your percentage and shadow panel, or maybe you just have that number coming out of your evaluate expression, plug into this number parameter. We can right click this number parameter and just call it percentage in shadow, just to, remind us of what it is. You can see it's 87.48 coming out. And now we can hold shift and drag down from the O output of Octopus, so that's the objective output, and plug into percentage and shadow. So now you can see it has two green lines, one connected to our reduced FSR and one connected to our percentage in shadow. So what this means is it's going to try to reduce both of these numbers. But if you think about it, as we reduce the FSR, we'll have less units, aka like less things that can self-shade the building, so our percentage in shadow is going to go down. But then we also have less FSR. So it's kind of this balancing act. So that's the first kind of input Octopus can take, just numbers that it wants to minimize. The second input that Octopus can take is a Boolean. So a Boolean as in a true or false. And if you remember last class, we set up this essentially limit switch that gives us a true if our reduced FSR is between 10 and between 6, so between 10 and 6. And it'll give us a true if that's the case, or a false if it's not. So what we can do is we can click on our O, so our objective output, and hook it up to this Boolean. So now you should have three green lines coming out of Octopus. First one to the percentage shadow, second one to reduced FSR, third one to the Boolean limit switch. The third type of data that Octopus can input is a legend. So simply, last class we had created this panel which we called Octopus Legend. We had plugged into a text parameter so Octopus could hook up to it. Last class we just had FSR, so floor space ratio. This class we have two things that we're considering. So we're considering the reduced FSR. We're also considering the percentage in shadow. So we can add another row to this Octopus Legend. So I'll double click on the panel. I'll just click to the right of FSR. I'll click enter to create a new line, and I'll just say percentage in shadow. And then I'll click out of the box like so. So then now I see 0, FSR, 1, percentage in shadow. I will again hold shift, drag out of the O, and plug it onto text. Now, the last input that's a little bit different is we could plug our, our joined mesh. We could plug that into the phenotype input. And essentially what that would do is it would just visualize this mesh in Octopus, but it's also going to make your computer run a lot slower. So I honestly never bother plugging this in. I just plug in my my genes and also my objectives. So once all those things are plugged in, now you should be able to double click it, and now Octopus will open. So now once Octopus opens, you can see that we have this three-dimensional diagram like so. It has the same navigation commands as Rhino. So with your mouse, you can hold your right mouse button to sort of rotate around. You can hold your middle mouse button and move around to pan. Or if you don't have a middle mouse button, you can hold shift and your right mouse button to pan. As well as you can zoom in and out with your scroll wheel in the middle of your mouse button. Or if you don't have a middle mouse button, again, you can hold control and hold down your right mouse button to zoom in and out. You can also switch to an ortho mode if you're so inclined with this little widget on the corner. As well as you have some, so Cecilia, Octopus. So if Octopus doesn't open, first of all, make sure, sometimes it has a bad habit of opening minimized. So if you double click on it, it's gonna look like, where is that? Now it won't let me do it. It's just gonna be a white bar. So just make sure that your Octopus isn't opening like that. I've also noticed it can be a little bit finicky, so just kind of see, like, mine's not really opening. Just kind of click on it till it opens. Oh, and there it is. It's up. See, there's that white bar I'm talking about. I always miss it. So look for a white bar. Shirley or Natalie, did that solve one of your problems? No white bar. Okay. I will... okay, I tell you what. I'll check your files. Send Rhino... emailing me your files and I'll check them during the break. Oh, I unplugged Boolean and it opened. Okay, well, we'll figure this out. So essentially, I wonder, maybe it won't open if the Boolean's false. I'm just gonna see something. Okay, so I have a Boolean value of false. Oh, weird. Okay, so if Octopus doesn't open, try doing this. Okay, so this is so strange. If Octopus isn't opening, you learn something new every day. Go to Parameters, Input, Panel. Take your Boolean, plug into the panel, and drag your panel above your gene pools. Yeah, and then right-click your gene pool, go randomize, and I think that you just essentially want to make sure your Boolean equals true when you first open Octopus. So essentially just randomize until your Boolean equals true. So true. And then double-click on Octopus. And now it opens. Well, there you go. You sort of learning things on the fly. It's weird. You never realize anything's wrong until it's wrong. Or you never realize how something works until it breaks. So I'm glad that worked for everyone. Okay, so now we're all in Octopus. Essentially, you're going to have some visualization options on the side here. So like the scale of your little boxes, as well as some opacity. But more important than that, you're going to have, essentially, you'll see that we have our two axes down here. So FSR and percent and shadow. And I'll go through what some of this means. But before we do that, I just want you to click Start. So you can see what's happening is we're getting these little dots. And what this means, these are solutions that Galapagos, or I keep saying Galapagos, Octopus has iterated through. So it's going through and it's kind of switching our gene pool numbers on and off and on and off in various combinations. And what it's trying to do is it's trying to switch them on and off in ways that gets closer to this center point, right? Because you'll notice that the closer we get to this center point here, the lower our FSR is going to be, but also, the lower our shadow percentage is going to be. So that's how Octopus is going to work, right? It's going to try to converge in the center point. Now, it doesn't know that a lower FSR is bad, right? Like Octopus is, a very smart function in certain regards, but it's also very dumb in kind of this human intuitive sense. So probably what we're looking for is more something along the higher FSRs, but lower shadows. So essentially what's going to happen is this solution here might actually be the best solution that we've found so far, right? So what we can do is, after Octopus has been running for a bit, it's kind of different than Galapagos. It won't really stop. You can just keep it going. But what you're going to want to do is you're going to want to hit stop/pause. Now, what's going to happen is we can look back into Grasshopper. We can click on these little boxes, right? And if we click on them, so left mouse button, we can go reinstate solution. And it's going to reinstate the call solution that it gave us. So, there's that solution there. We can reinstate solution there. It's going to give us the solution. We can click here, reinstate solution. It's going to give us that solution. So essentially we can look back. Now, what we can do if we like one of these solutions is, let's say I reinstate this solution. I really like it. And I want to sort of tell Octopus, hey, this is the kind of solution I want. I don't really care about this stuff as much. I can click on this solution and I can go mark preferred OBJ. And now when we hit start again, this is sort of going to be brought forward. The other thing we can do here is we can click on this little checkbox that's hidden but next to diversify parameters. And what this is going to do is it's going to bring up the z-axis. So we can see now we have genetic diversity. And what this means is it means that for certain values, so like let's look in the plan view here, you can see for certain values we're pretty close in both our FSR and our shade value, but if we look at it in elevation, essentially, they're very different. So that's what that means. That's what genetic diversity is. It means that this iteration down here is extremely different than this iteration up there. So we look at this iteration right there versus this iteration down there. Those are going to be as far apart in terms of on-off patterns as can be. Once you've sort of tagged, a solution you like, so I'm just going to unpreview the diversify parameters. I find it easier to look in 2 dimensions. Once you've tagged a couple of these, maybe you look at this one, you're like, oh, that's also kind of cool. Right now, when you first run it, you're not going to see much of a difference, to be honest. Once you've sort of tagged a few of these that you prefer, then you can start the simulation again. Now, there's a few options below the start button, stop button, reset button that we might want to consider. So the first one is elitism. And essentially what this means is it means how close to these chosen solutions do we want to keep future solutions? So in other words, how strong is the selection for these solutions? So if we set elitism to, like, let's say 1, it's going to, create solutions that are much, much closer to this solution right here. But the reason why you don't want to do this, especially in the earlier stages, is we haven't let this genetic algorithm run for, very long. And there might be a way better solution than this one, somewhere way out here that we're not aware of yet. So we don't want to essentially limit our results. There are some other things, though, we can play around with. So mutation probability, so the probability of each parameter value to be mutated. If we're really, not keen on many of our results right now, we can turn this up. And essentially what this means is for each iteration that Galapagos Octopus goes through the slider configuration, for each slider, how likely is it that it gets switched from a 0 to a 1 or a 1 to a 0? So if our mutation probability is 0.5, it means for each iteration, it has a 50-50 chance of whether that switch is going to be flicked or not. The mutation rate doesn't actually mean much for this particular, optimization, because we're just switching between 0 and 1, right? So there's no values between. But let's say we're going between 0 and 10. Mutation rate would mean a value of 0.5 would mean 1 can go to a maximum 5, or 5 can go to a minimum 1, whereas a mutation rate of 1 would mean that a 0 could turn into a 10. Finally, the crossover rate is essentially how many of the iterations which don't really cut the muster are carried over into the new iteration. If we think about this in a genetic term, on which this algorithm is based on, I guess, like genetics, it means or evolution. It means how many of these poor little critters just get eaten up by nature. So you can change some of these. There's some other algorithms. Honestly, I usually actually always keep these to default. If you want to read the octopus white papers published by ETH, you can do so and read about these different algorithms. I just leave these as the same, and then I will play around with these variables there. And essentially, once you're happy with that, you've picked a few more preferred options, you can just click start. So now what it's going to do is it's going to keep on solving. And you can see that our preferred solutions are now, they're really the only ones that were carried forward. So does anyone have any questions about this, about what Octopus is doing? Okay, so what I would suggest, for your assignment 2 is consider this kind of stage in Octopus to be your last step for assignment 2, right? So essentially, once you've found a solution in here that is, as good as it can be, so the highest FSR with the lowest amount of shadow, maybe let your computer run for a few hours, check in on it like after you're finished watching one episode of whatever you're watching, and then choose a few good ones, let it run again. Once you get to a pretty good place, then you can just go stop for good. You can choose a solution that you like the most. I'm just going to choose one arbitrarily, and then you can just go reset. And the reason why you want to go reset, you can also export your data, but we won't worry about that now. If you don't click reset, all of those iterations, including their geometry, will be stored in your computer's memory, and you'll notice that Grasshopper runs much slower. So just make sure to click reset when you're happy with your solution. And then you can just exit Octopus, and then right click and go disable. And then there is our solution. So I mean, if we look at this, 86% in shadow, so we didn't get much of a gain. Reduced FSR is 9.6 FSR. So I mean, if you were doing this in real life, it's good because you can assure your client that you'll meet the FSR. But you're never going to get this perfect Bjark angles diagram thing where you're like, rotate for maximum sun. Like, all units get maximum solar exposure. Like, in real life, it just doesn't work like that. But what Octopus can help you do is it can help you sort of look through different iterations and kind of evaluate which one is the best trade-off. So with that being said, what I'm going to do is we will take a 10-minute, well, maybe let's say so a 10-minute break till 7:37, I'll say. And in that time, I will try to address, I think, I'm not sure if I got any emails, but I'll try to address some of the questions sent my way. I don't think I got a question sent my way. So if anyone has a question, I'll be around to answer it for the next 10 minutes, but otherwise we'll just have a break till 7:37. Thanks. And so resume. So what we are going to do now is we are going to bake our meshes. So if you remember what we did for our intersection, I'm just going to preview off a bunch of stuff here and open up the chat again. Okay, so I have my geometry here. I'm just going to change my floor height so my FSR is still working. What we're going to do is you have this mesh that's coming out into the mesh join. We're going to bake this. Or if you can't find this, essentially what we're doing is we're going to the call pattern that's coming out of our gene pools. So this is after you've optimized it. And this is what you'll bake for assignment 2. You're just going to go to geometry, mesh, plug your call pattern into your mesh. And then what we'll do is I'll just create a new layer. So I'll go new layer. I'll call the layer, you know, Voxels. Maybe I'll record my FSR. So I think I'm 9.3 FSR. And then I'll bake these meshes to that voxel layer. Just closing octopus there. So I'll right click this mesh and say bake. And then I'll bake it to the layer voxels 9.3 FSR. And you might want to group this. So group, yes, please. And, you know, at this point, you're sort of done this script. It's a good time to save your Grasshopper file. So now I can just close that. And I'll close all this other stuff too. So what we have here is our baked voxels. Now, why do I have this red stuff? Oh, it's this. Okay, so you're going to have something like this, and this is what you're going to hand into assignment 2. So you're going to hand in alongside your one Grasshopper file, you're going to hand in these voxel meshes as well as your solar mesh. So I want to see both of these things, so your voxels and your solar mesh, and this is what we're going to use to move forward. So once we have this, though, we're going to start to populate this with geometry. So if we think about the first lecture, so I'm just going to go back to the very first lecture file, this presentation I gave here. We're talking about taking these voxels and filling it with geometry, right? So it could be this Ricardo Bofill thing, a Zaha Hadid language, Kazuyo Sajima language, crazy Mark Foster Gage, or a very traditional temple language. We're going to take these geometries and we're going to fill it with stuff. So right now we're at this point. We're at the geometry to be filled stage. Now, to do that, we essentially need to classify this into different conditions. Now, this logic that I've set up here is based on an algorithm called marching cubes. And essentially what marching cubes is, I'll actually just look up a diagram right here. It is something that was used in old MRI scans. So essentially what goes on is, you know, some sort of microwave shoots through a person's head or through their body. And essentially, if tissue is of a certain density, that microwave or ray, what have you, shoots back to the sensor, and it gives a true or a false, right? So a true if a dense tissue was hit, a false if the ray just went right through and wasn't reflected. Now, the problem was, okay, we have this kind of this field, right? So if you think about the LiDAR, it's the same as LiDAR. We have this field of points. The only issue is, how do we take this field of points and make actual geometry out of it? So some very intelligent mathematicians in the mid-90s, they said, we can designate these points in, I believe it's 64 different configurations. So we can look at each cube and we can say, okay, if there's a cube, so we can look at this that has a on, and the rest are off, it means we need to draw a mesh face like this and a mesh face like this. If all points are off, there's no mesh face. If only one is on, then we draw a mesh face like this. So that's sort of what we're doing. except instead of taking, you know, all these 6 points and essentially drawing a mesh face instead, what we're doing is we're going to try to classify these different voxels in terms of the relationship to their neighbor. So for example, what we're going to do is we're going to look at each voxel and we're going to ask, is a face exposed or not? So we're going to test the center point of each of these voxels, and we're going to say, does this center point touch a neighbor? So in the case of, like, let's look at this voxel. I'll just ungroup these right here. In the case of this voxel right here, we would say that if, again, we have a plane, so let's say this is local south, we would say the south face is exposed, the east face is exposed, the west face is exposed, the bottom and the top are exposed, and only one side is connected to a neighbor. So this face right, oh yeah, I forgot that my cursor is an inch above. So this face right there, that face right there that's behind, that one is connected. So what that means is we have a condition like this one on the end. So this condition here, we can say whenever we have a condition like the one we were just pointing to right there, we can replace this geometry with a more detailed geometry like this. However, let's say we have a condition like that where it's exposed on one. So let's look at this. Let's look at this voxel right here. So in this case, it's exposed on its east side, its south side, its west side, as well as its top side, but its bottom side is also covered, or it shares a face with its neighbor right below it. So in that case, we can classify it in a different way. We can say, okay, well, now we need something that essentially, let's say this one right here, which is exposed on 3 sides, it's exposed on the top, but underneath, if we look at it, it has an interior space, for instance. And we can go through and we can sort of classify these different voxels like that. Now, what I've done is if you go through the new site model, under the demo layer, there's a layer called pieces. And if you click on pieces, instead of the 64 different configurations of for the marching cubes algorithm, I have defined, I think it was 1, 2, 3, 4, 5. So yeah, so 23 different configurations that could occur in a stack of voxels. Now, I've classified these configurations with just names I've thought of. So, for example, you have an interior roof. So I've called this an interior roof right here. So I've said this condition, the interior roof, exists where there's conditions like, let's say, I don't know if I have an interior roof here. You can imagine that this one right here, so that one right there, if there was a voxel right there, it could be an interior roof, right? The next one I have here is the interior. So this is a voxel that's surrounded on all sides, so it's a totally interior space, as well as interior bot. And bot is just short for bottom. It's, I don't know, like an abbreviation that I've kind of used for a long time, so it's kind of second nature. So essentially this condition will occur wherever it's surrounded by neighbors, as a neighbor on top, but its bottom is exposed. Now, this condition here is the column roof, and what that means is anywhere you have a condition like, let's say, I'll make a column roof. You have a condition like this, where it shares a floor, so it's not floating, it's exposed on all 4 sides and the top. Essentially, you can think of this as the top of a column, so it's a column roof. So that's why for my detailed geometry here, I have modeled essentially what looks like the top of a lookout tower. So wherever we get that condition, we'll put this lookout tower. Likewise, we have a column. So if it has something above, something below, but it's still in the column. A column bottom, so something above, it's kind of the same as the column. And then finally, a weird condition, a column floater. If there is a UFO above your building and all sides are exposed, you can assign a condition like this. I would encourage you guys to assign, well, maybe get rid of any floating pieces, but if you want a floating piece, maybe make it like a hot air balloon or a UFO or something. Furthermore, we have tunnel conditions, and the way I've classified tunnel conditions is essentially any time you have something where it is connected on two sides. So, for example, right here, where it has a neighbor right there, but it's not connected on that face, it's not connected on that face, that is kind of what I'm calling a tunnel. So if we go and look at the tunnel examples, you can see that's what's happening. So they have, you know, an exterior face on that side, an exterior face on that side, but they're open on these two faces. We have corner pieces, so that makes sense. It's just corner pieces. We have side faces, so in conditions like this, where, you know, it's kind of, or like this, where, you know, it's surrounded on all three sides, only has one exposed face. That's like a normal building wall. So those are what I'm calling the side faces. And then finally, the last piece, the first example I showed you, what I've called nubs. So just little things that stick out. They have three exposed side faces, one hidden face, one top, one bottom. So if you're working with a marching cubes algorithm, essentially what happens is you use what's called a lookup table. But what we're going to do, is we are going to essentially use all our Booleans, or we're going to use Boolean functions to kind of suss out which voxels are which. And I saw that Natalie asked the question, do we hand in a landscape element too? Yes, of course. So the landscape element is a part of the project. I just forgot to mention it because I was looking at the tower here. So please, as per our Bison class, adjust your landscape around that building. So that is a portion of the assignment. So what we're going to do is we're going to start this class, and I'm going to get only part of the way through. Again, I don't think we'll have time to cover monolith. That's a-okay. And then we'll pick this up on Monday. But what we're going to go through is we're going to make a bunch of rules to choose these different configurations. So I just baked my my voxels from the last part. So before the break, you know, we did the solar optimization. I baked these voxels as meshes. You can do that, or if you want, you can, if you're using the class file, you'll see there is a layer called tgfsr voxels 9.5 FSR. You can always work with this file here. Another thing I should mention is this is sort of my raw output. When I made this tgfsr 9.5 FSR layer, I took a raw output like this, but then I went through and I kind of, you know, massaged it into something that I thought was a little bit more interesting. So I got rid of some conditions I thought maybe weren't as practical, and I added this little floating bit just so we could see an example of it. So feel free to take your raw output of your voxels and sort of edit them in Rhino simply by, you know, copying them like this. So transform copy, you know, you can do this. So feel free to edit your voxel pile after the fact. Okay, so we're going to start a new, I would suggest starting a new Grasshopper file just so you can keep these things separate. So does anyone have any questions before we start? Okay. Now I will say, here are my notes, and you may look at this, and this will be the biggest file I've ever taught in a Grasshopper class, and you might think like, oh my god, this looks huge, and it is kind of big, but the thing you need to know is that all of these pieces are kind of repeated elements, and you'll see what that means when we do it. So don't worry, this looks much worse than it is. We're going to be doing a lot of copying and pasting. But the first thing we're going to do is we are going to start out with essentially finding the neighbors. So first, what we need to do is we need to essentially, I'm checking my notes. We need to reference all of our boxes here, so all of our voxels. I'm just going to move this over so it's out of the way. Okay. So first thing we're going to do is we're going to reference all of our voxels. So let's go to param, geometry, mesh. And I'm going to go set multiple meshes. And what I'm going to do is the layer that you've baked your voxels onto, right click that layer and go select objects. So you can see I've selected all these meshes, and then hit enter. And that's just a way to select all those meshes at once. Now this parameter, this mesh parameter, we can right click it and we can just call it voxel input, like so. Now, what we're going to do is we're going to recreate essentially a bounding box for all of these meshes, because essentially what we need to do is we need to grab those corner points again to get the center faces. Now, because we just found the center faces in our last Grasshopper file, we can recopy that definition, so we don't need to recreate it. But to create our plane, I'll show you another way of creating a plane. So maybe what I'm going to do here is I'm going to go to geometry, point. I'll put it on the canvas like so. I'll right click this and then I'll go call this bounding box points, and then I'll call x/y/z. And essentially what I mean here is I'm just going to pick 3 points that correspond to the edges of one of my voxels as a way of creating a plane for our future bounding boxes. So I'll set my view to be shaded just so I can see the edges of this voxel. So what I'm going to do here is I'm going to right click the bounding box points. I'm going to go set multiple points. I'm going to make sure that type equals coordinate. I'm going to make sure that my vertex snap is on. So that allows you to snap to the vertices of meshes, or in this case, the corners of our voxels. And just somewhere kind of in what you will consider your local south. So, you know, for our site, this is south, you know, straight up like that. But in my case, I'm going to consider this edge here the local south. So what I'm going to do is I'm just going to choose my X, Y, Z min, so this corner. Then I'm going to choose my X max, that corner. And then what I'm going to do is I'm going to go underneath, and maybe what I might actually need to do is I'll go view wireframe, just so I can click this last corner, so the Y max. So X, Y min, X max, and then Y max. So essentially I'm just choosing those 3 points. Hit enter. And now I can see I've chosen those 3 points. Now, what I can do is I can go to vector, plane, and then I can go plane 3 points. Now this requires the origin point, the x direction point, which is the second one we selected, and the orientation point, which is the y direction point we selected here. So what we're going to do is we're going to break out these 3 points, and to do that we'll go sets, list, list item. We'll plug our bounding box points into our list. So this gives us our first point. To find the, or to grab the second and third point, we can just zoom into the list item, click the little addition symbol, click the little addition symbol again, so we get I, so 0, 1, 2. And then we can just plug I into point A, 1 into point B, and 2 into point C. And now you can see that just gives us a nice plane that is oriented to our voxels. So that's another way of making a plane, and this will work quite nicely for this sort of geometry. Now let's just group this, keep everything nice and organized. I'll right-click it and call it plane for bounding boxes. Okay. Like so, perfecto. Now what we can do is we can create bounding boxes for each of these objects. So let's go to surface. We can go to primitive and then bounding box. Now the content is going to be our voxel input, so all our referenced meshes. Let's plug that into content. And the plane will be this plane we just created. And for this, we'll leave the bounding box at per object. So in the past, we've right-clicked this and gone to union box, which would create one big bounding box. But for this, we actually want one box per voxel. So we'll just leave it as per object. And now we have all of these bounding boxes. So I know that we kind of had bounding boxes before out of our previous step, but the thing is, for huge grasshopper definitions like this, you kind of want to break these steps apart so your computer doesn't, scream out and get all angry at you. So now that we have this, essentially what we can do is we can just go back to our previous grasshopper definition we had and copy the center points definition. Because remember, we had already kind of figured out the center points. So let's go to File, Open Document, and just navigate to your document. Now, if for some reason you were like, okay, I baked my mesh, sucks to that definition, I'm going to get rid of it, I will save where I'm at into the Dropbox right now so we can all be on the same page. So what I'll do is I will just connect this to there. I will delete all of my notes. And then I'll just save this in the Dropbox in today's class so we're all on the same point. Oh, it's not Dropbox. I'll save it as Voxels Part 3. Okay. So I've saved this as Voxels Part 3. Okay. So what I've done there is essentially I've just copied and pasted this section of the definition we were working on earlier. And essentially, if we remember what this one does, is it just takes a bunch of boxes, it decomposes them into their corners. After that, it averages out those corners to get different faces. So if we refer to this diagram here, for example, it averages the min point with the x max, y min, z max to get this face point right there. So what we're going to do is just take our bounding box per object, plug it into this definition we'd already made, I'm going to delete this point that I have coming out right there because we don't really need it. And I'm going to right-click this group and just go ungroup. And then I'm just going to make sure that we kind of have a firm grasp on what we're dealing with here. So I'm just going to look at one box here and just sort of look at the points we have. So what I mean is, let's look at this first point average. So preview. So this first point average is what we can call the south face. So what we can do is we can go params, geometry point, plug this average into this point, and I'm just going to call this south face. And this is just so we can keep track of what faces we're dealing with, because you'll soon see that it's something that will be very helpful for us. So I'll preview off the south face. This face here, if we're thinking of this side as our south face, is never east. So we can go to geometry point, plug our second average in there. We'll call it east face. This one here, you can see it is our west face. So we can go geometry point, right click this, call it west face, preview off that, and then we'll preview off this, and this is going to be our north face. So right there, that will be our north face for all of these. So let's go geometry point, put down the canvas, right click it, call it north face, like so. So now we have our 4 side faces. Now what we need is our top face and our bottom face. So if we go back to our diagram here, to get our top center point, we can go min, min, max. And then this corner here is going to be max x, max y, max z. So min, min, max to max, max, max. So what we can do is we can look at our 3D view just to, keep this fresh in our brains. We can go to math, utilities, average. We'll just grab 2 of these because we'll need the top and then the bottom. So math, utilities, average. So to get this center point, we're going to go min, min, max. So that is corner, I think it's, so let's look for min, min, max. So min, 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 max, min, min, max, max, min, min, max, min, 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 max. So corner E. So plug in corner E. That's the right corner there. And then we want max, max, max. I believe that's F. No, G. So G is max, max, max. So plug in G. Now you can see that gives us our top center point. So just to keep track of that, let's go to parameters, geometry point. Take our arithmetic mean, plug into point, right click that point and call it top face. We can preview off this. And then finally we need our bottom face, so that can be the average between, let's say, min, 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 which is corner A. So take corner A, plug it into our average. And then I believe it's corner G, which is the mislabeled one. So I believe it's max, max, min. And I was wrong, so let's right click this, go disconnect corner G. So just have corner A plugged in, and then let's look for, that would be max, max, min. So min, 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 max, min, min, max, max, min. So corner C, so A and C. And then there's all our bottom faces. Now we can go to param, geometry point, and I'll plug that in. I'll right click this component and I'll call it bottom point. And I'll preview off. So now what we have is sort of the same thing we did before, except we're grabbing all the center points of all the faces of the voxels. I'm just going to refer to my notes. And okay, perfect. So what we're going to do now, actually, does anyone have a question now before I move on? I'll actually save this file where I am right now, just in case some of you weren't able to open it in the time that I said. So I'll just group those. I'll call this group all faces of voxels, and then I'll save this in the Dropbox. So if you need it, it's under voxels part 3. Okay. Okay, so excuse me. So apparently my undo, oh, it's because it was undoing all the typing. Okay, good. I still have my notes. Okay, so what we are going to do is to test whether or not a face is exposed. We're simply going to test if there's more than one of each point in all of the points here. So what I mean by that is we can essentially say, okay, this top point here, does it share space with any other point in all of these points? And for this we can say no, because there's only one face at this position in the pile of voxels. But if we go to, let's say, I know it's kind of hard to see, but here, let's do this. But this green point there, and I'm aware the mouse offset, so the point you can see me pointing to is the correct one. This point here, you can see that it will actually be shared by two faces. So therefore, there's 2 points here sharing the same location in space. So what we're going to do is we're going to test for each of these points. Do you share the same location in space as all of the points? So that's the algorithm we're going to set up now to test if a face is exposed or not exposed. So what we are going to do is we are going to plug all of these into one point again. So we're going to go to, let's do this in a kind of organized way. Let's go to set tree merge. So set tree merge, and let's plug in our let's plug these in and kind of let's plug them in the northeast southwest. I know that we've sort of done these in a different order. We went southeast west north, but I think, you know, I always remember that little rhyme, like never eat soggy wieners. I was taught in Boy Scouts way back in the day to remember northeast southwest. So what I'm going to do is I'm just going to reorganize my points into northeast southwest, like so. So northeast southwest, and then top bottom, and we're going to merge the points in this order. So north will go into data 1, east data 2, south data 3, west data 4, top face data 5, bottom point data 6. Now to reduce or get rid of this dangling D7, don't really need it. I'll just zoom into the merge component and just click the subtraction button. So now what you can see is we have a bunch of lists which have 1 or 6 points per list. So it's the 4 sides, top, bottom. So they're sorted by their voxels. What I'm going to do is I'm going to grab 2 point components. So I'll just preview off this. So I'll go to parameter geometry point. Again, parameter geometry point. And I'll plug the merge into both of these. And I'll preview off this. Now, remember, what we want to do here is we want to compare each point to all points. So if we think about our data management, what we can do is Grasshopper, we can take advantage of the way Grasshopper manages data. And right now, both of these lists have 6 points per list, right? So each list is going to have, there's a list, and then there's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. If we are to measure the distance between these points, essentially what Grasshopper is going to do is say, what's the distance from there to there, there to there, there to there, there to there. It's going to match point for point, and because these are all the same points, the distance is going to be 0. What we want to do instead is graph this list. So we hover over it. Now you can see there's 1 point per list. We still maintain the order of the data, and now instead of it just being a leading dangling 0, that first number in our path actually has value to it. So what I mean is 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5. In each of those paths, the first value refers to the box. So you can think of that 0:0. The first 0 means box 0, point 0. The next list is box 0.1, then box 0.2, and then you move on all the way to the end where it's box 975.5. So that's what it means, but all these points are in their same, or in their own individual list. But since we want to compare them to all the points, what we do for this second list is we right-click it and go flatten. So now, oh, not graphed, flatten. So up arrow, down arrow. So now if we look at this list, it's 5,856 points in one list. So now what happens is we have all of these own points in their individual list. Now they share one box like this. So the first 0 corresponds to this big box. The second number corresponds to each point in its individual box, like so. And then for this flattened list, what's happened is all points are in one big box. So here's our points, all in one big box. So now what's going to happen, instead of going point for point measuring distance, this point's going to measure the distance with all of these points, because Grasshopper is going to match list for list, or you can think of it branch to branch, box to box, etc. And then this point's going to match all these points. So that's how we compare each point to all points. So does anyone have any questions about that? Because that's kind of a fundamental thing of how we're testing. Okay, so with that now, what we can do is we can measure the distance. So we can go to vector, point, and then we can go to distance. So compute the Euclidean distance between 2 point coordinates. Distance A, or point A, will be our grafted points. Point B will be our flattened points. And it might take a second, might take more than a second. Okay. Now, if any of your grasshoppers have crashed now, I can actually think of a component that might run faster than this. So if your grasshopper is still frozen, I apologize. What I'm going to do to make it go a little bit faster is you could also try disabling that one, or you could, instead of distance, you could go vector, point, closest point. And I think this will run faster. So put your grafted points into points, your point cloud into cloud. And yeah, that component runs a little bit faster. So closest point can also work. So why don't we go to closest point instead of distance? So I'll save this file in the Dropbox again. And for those of you, if your computer's frozen, you can just, I'd wait for it to unfreeze. But this is probably one of the biggest calculations we'll do on all class, but it's a necessary one. So I'll just save in the Dropbox in case you want to use this. Okay. So now using closest point, our grafted points are going into point, our flattened points are going into cloud. Essentially, what we're concerned about are all these distances. So if I grab a panel, so parameters input panel, I look at all these distances, I see a 0. I see a bunch of zeros. And you know what? Actually, this one won't work. Sorry. I'm not following my notes again. Let's delete this one. What we actually want to do is go closest 2 points. And the reason why we want to do that is if we choose closest point, then it's just going to choose itself. So my mistake, it happened. So let's go to vector point closest points. So vector point closest points. Now, before we hook up anything, let's right click on count and change the count to 2. So make sure the count's 2. We only want 2. Take our grafted points, plug into point. Take our flattened points, plug into count. Or not into count, into cloud. So point into cloud. Again, it's going to take a second. And now that's going to give us what we want. So now I'll save this file in Dropbox. So sorry for that confusion. That's what happens when I try to optimize things on the fly. But I think that's going to be the best way to go about it. So essentially what we have here is our grafted points going into point, our flattened points going into cloud, and our count equals 2. So what this is going to give us is for each distance, it's going to give us 2 distances. So let's go to parameter, input panel. And while your computer's unfreezing, I will tell you what we're doing here. So if you look at the first number, it's always going to be 0. And the reason why that is since we're comparing each point to the cloud of points, the cloud of points is also going to compare, or it's also going to include the original comparison point. So for example, this point here at the very, very top, so that one very at the top there will also be included in this big set of points. So that's where this 0 comes from, right there. What we're more concerned with is values that are 0 in the second number. So the second closest point is also 0. So we see 0. What we're also concerned with is these values that are extremely small. So 0.000011. Now, Rhino has something, and don't worry about following along with this. If you go to properties and units, you're going to see there's absolute tolerance under your units. Now, for a computer program to calculate absolute values, or like, absolute units, to very, very exacting degrees, it takes a lot of computational power. So what Rhino does when it calculates the position of points, it kind of rounds it. And that's why we get these kind of super, super close values. So whenever you see a value that has more zeros than your absolute tolerance unit, essentially you can chalk that up to just a rounding error in Grasshopper. So Grasshopper's tolerance is higher than Rhino's tolerance. And as a result, any extremely small number like this is as good as 0. So we need to take this into account. So what we can do is we can test the distance for both of these. Well, actually, we'll just test it for the second value. But instead of saying equals 0, we'll go less than a very small number. So what I mean is we'll go to set list item. We'll take our distances output, plug into the list input. I can just preview off all of these. And we'll set our index to be 1. Because if you look at all of these, we know in Grasshopper, the first item in each list has an index of 0. Second item's 1. We always want the second item because the first item is going to be at the self-same point. So let's right-click on index, go to set integer equals 1. Now the distance, you can see when we look at the item out, it's always going to be that second value. So 0. that means this space is covered. It shares space with a neighbor. 5, it means its closest neighbor. Maybe it's this face here, its closest neighbor is there. It means this face is exposed. And our algorithm sorting what kind of voxel this is needs to take that into account. So what we're going to do is we're going to set up a test. We are going to go to math operators smaller than. So math operators smaller than. The first number will be our list item. The second number will be a very small value. So we can go to parameters, primitive number. And then we can just call this small number. And we can set our number. It just wants to be something like 0. And then our tolerance in Rhino is 3 zeros and then a 1. So we can just set it to that. So something like that, 1/1000th, for instance. Sometimes you might want to set it to even 2 zeros, so, you know. But I'll set it to that because it seems like most of our numbers down here, like these two numbers, are smaller than that number, which I'm typing in. And then click Commit Changes, plug that into second number, and this is going to give us a bunch of trues or false. So we can say smaller than or equal to, and you can say true, false, false, or true, false, true, 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 false, false. And essentially what this means is whenever it has a false, it means that it is sharing a face with another voxel. So that's what that means. So what we're going to do now is we are going to use this information to start to classify these voxels. So let me just refer to my notes. While I'm referring to my notes, we can all group these components, right click, and then just call it testing if voxel shares a certain point / face. So, essentially what we want to do, and I just saw, if you see this huge note I left for myself, invert this Boolean to keep exposed faces. What that means is, it's been a long day, essentially, if it's false, that means the face is exposed. It's not overlapping with the neighbors. So what that means is we want to keep the faces that are exposed. So to invert this Boolean, we can simply just go to primitive Boolean, take our or equal to, plug into the Boolean, right click, and go invert. So essentially all this is going to do is, if we look at the output, you can see the falses become trues. Let's go. So false goes to true, and true goes to false. And we're just going to do this because we want to keep the faces that are exposed, because the way we're going to classify these little shapes here are by exposed faces. So now what we can do is we can simply kind of create classifications. So what we'll do is we will go to trim tree. So we'll go set tree trim tree. The tree we're going to trim is the Boolean. The depth will be the default value of 1. And what this is going to do, if we look at the output, so I'll grab a panel, I'll look at the output of the Boolean. You can see what it's doing is it's just giving us these trues and falses in their own individual lists. So it's organized by voxel number, then point number. But what this trim tree is going to do, if we look at the output of this, is it's going to, well, it got rid of 1 0 there, so actually to fix it even more, what we need to do is we can right-click the input of tree. Actually, let's right-click the output of Boolean, go to simplify. So now we have voxel number, then point number. You can see that it gets rid of that secondary list. So now the trues and false corresponding to the points of the voxels are all included in a list which corresponds to each voxel. So now essentially what this means is for each face, for each voxel rather, we have the 6 faces. So north is exposed, east is exposed, south, west, top, bottom, they're all exposed, whereas for this voxel, north is covered, east is exposed, south is covered, west is exposed, top is covered, and bottom is exposed. So that's what this means. Now I'm going to leave it here. I will save this file in Dropbox again, just so we're all at the same place. And we are going to pick this back up on Wednesday. So tonight I will update the assignment 2, but in short, assignment 2 was originally due, I believe, this coming up Monday. Yeah, so assignment 2 was due on Monday. Instead, now it's going to be due on Wednesday, July 15th, just because the class took one more day than expected. Also, Nicholas and I are going to get your marks back to you this week, so you can take the comments from assignment 1 and use them to improve perhaps some of the components of your assignment 2. So look out for your mark from assignment 1 this week. So thank you very much. If anyone has any questions, I'll stick around for a bit. But rather than that, that will be the end of this class, and I'll see you all on Monday. So feel free to email me and Nicholas as well. Thank you.